Hello and welcome to Train Signal. You are watching Managing User Resources, Quotas and Permissions. It's not uncommon today to see laptops with over 150 gigabytes of hard disk space, and even more on desktops. Still, even as users store larger amounts of data, the possibility of exhausting your hard disk space always looms nearby. If you apply that to an enterprise setting, you can see where the need might arise to monitor and control how much hard disk space your users can have. So in this lesson, we'll talk about how Linux handles disk quotas and how you can implement them on your own network. Managing your user data also involves setting permissions for what they have access to. In Linux, this is handled with file permissions and ownership. We'll review how file ownership is determined, how to change it, and how to set the permissions that determine who can access those files. Let's start first with disk quotas. I can already hear the arguments. Disk space is plentiful, you might say. Hard disks are cheaper than they've ever been. And while both these statements may be true, in a corporate setting with thousands or even hundreds of thousands of users all consuming disk space, this is an all too real an issue. Take for example TechCorp, the company that we outlined in our course scenario, and they do application development. So they've got thousands and thousands of lines of code per each application they develop, along with any associated multimedia or graphic files. Their data center is literally bursting at the seams. As part of their transition to Linux servers, they want to implement disk quotas that will help better manage their escalating hard disk costs. To enable quotas, you of course need the package, and you also need a kernel of 2.6.x or higher in either ext2, 3, RiserFS, JFS, or XFS file system. You'll remember these from our Linux file systems lesson. Now, Quota doesn't normally come pre-installed as part of the base installation, but on our Fedora system, you can check to see if it is with the rpm-qi quota command. If it isn't installed, we can install it using the yum command we learned about in the package management lesson. Let's switch over to a terminal window and give this a try. Let's launch a terminal window, Applications, System Tools, Terminal. And if you recall, we need to have root privileges in order to install software, so let's go ahead and do that first. Type in SU for switch user, enter. And enter your password. And now we have root privileges. First, let's make sure that Quota isn't installed. We'll type in rpm space -qi space quota. And we see that the package is not installed. So if we want to install it, let's type in yum space install space, oops, forgot the other L, quota, and hit enter. And you'll see it go through and load the package. We'll say yes for OK. Now that that's complete, let's go back to our presentation. Now the next thing that you would need to do is to open your etc fstab file and then add the user quota and group quota parameters to the mount options for any partition where you want to use quotas. Then you'd have to restart your system. So a typical line would read dev sda3 /home space ext4 followed by usr quota, grp quota. Now that we have the quota package installed, let's move on and talk about how to configure it. So we've told our Linux system that we want to use quotas. Now you enable it with the quota on command. And the next step is to configure the settings for our users and or groups. You do this with the add quota command, and the syntax is add quota space user or group name. Now this will open the Vi editor that we covered in the GNU and Unix commands lesson. In this file, you can change the hard and soft limits. Hard limits is the maximum number of blocks or inodes that the user can use, while the soft limit allows the users to temporarily exceed that limit, but with a warning, and they have a grace period, which is set per file system, not for individual users, and when that period runs out, the limit will become a hard one. You set the grace period with the -T option, so it would read add quota space -T. To periodically check that everything is working properly with your quotas, you use the quota check command. And entering quota by itself can be used to display information about your file system. The -G option displays information about groups. -L says to omit NFS file system information from the report. And -Q will only show file systems that are over their usage limits. And finally, rep quota performs much the same function, and it uses the -A option for all information. Both tools are good for tracking your disk usage. Now we'll take a look at file permissions. Ownership of a file is designated by the user that creates it. So essentially, if one of your users logs in and creates a file, they own it. You can view ownership information using the ls command with the -L option. Let's take a look at that. First, let's clear things up with the clear command. Then let's type in cd for a change directory and documents, so we can move to our documents directory. Now let's type ls space -L. The list outlines the permissions in the first column that you see here, the username or file owner, then any group name, and some other file information. If you want to change the ownership of a file, you use the chown command. Now only root can perform this operation, as you could imagine the chaos that would ensue if any user could change the ownership of other users' files. The syntax is chown space options space new owner new group space file names. You'll probably very rarely use any of the options, which you can review on the chown man page. But one that you might use is -R or --recursive, which makes the change to the entire directory tree. So if we wanted to change the ownership of the file cfiles.txt to Nancy and the group to techdev, the command would read chown space Nancy techdev space cfiles.txt. If you noticed, we changed both the user and group ownership with one command, but there may be times when you just want to change the group, which can be done by both root and users as long as the user is a member of that group. You do so with the chgrp command. It has the same options as chown. Okay, let's switch back to our terminal window and try out this command. For this exercise, I've created a dummy user, and we'll cover how to do that in a later lesson. For now, though, just follow along. Do you remember the command from our GNU and Linux commands lesson that lets you create a dummy file? If you said touch, you're right. Now we should still be in our documents directory, so I'll type in touch, T-O-U-C-H, space, test file, .txt. And at the prompt, again, let's type in ls-l. And we can see our new file there. Now that file, as you can see, is owned by root. Let's say we wanted to change it to our dummy user. We would type in chown Nancy and the file name, testfile.txt, and hit enter. Let's type in ls-l again. Actually, if you remember from a previous lesson, we can use the up arrow key to access our history. And there's the command. So let's hit enter. And we can see right here that our test file's owner has been changed to Nancy. Ownership only represents part of file access control, essentially who owns which files. The other half of the equation must address who can or can't access or modify those files. Now, file permissions are much trickier than ownership, so buckle in. Permissions are assigned to 3 resources for each file and directory. Owner is the owner of the file, group represents the group that has ownership of a file, and other represents every other user on the system. There are also 3 permissions as highlighted in this table. Read, with the lowercase r as the symbol, allows users to open and view a file. Write, with the lowercase w, lets users open, modify, and save a file. And execute, with the lowercase x, says users can run an executable file. So you have 3 permissions, read, write, and execute, for 3 types of groups: owner, group, and other. With me so far? Okay, let's move on and take a look at a typical permission string. Take a look at the image on the screen. It's the output from the command we completed on the ownership slide. The first character you see on the 3rd line is a dash. That's the file type code, which tells Linux if the file is regular data, a directory, or a special file. We'll review those in a moment. And that string of 9 characters with the R's and W's is the permission bits. And those bits are broken into groups of 3, containing 3 characters each, which determine read, write, and execute permissions as follows. The first group is for owner, second is for group, and third for all other users on the system, and you'll hear this referred to as world permission. These are called permission bits because the information is stored in binary format, expressed in octal or base 8 form, and a base 8 number is of course 3 digits long. So if we put that all together, we see why the permission string is 3 digits, with the first for owner, second for group, and the last for other. And you can determine the permission's octal number by adding their base 8 numbers, or 4 for read, 2 for write, and 1 for execute. So using the example on the screen, the permission would be owner 4 plus 2 for read and write, the same for group 4 plus 2 for read and write, and other only has read, which is 4. So we would have a value of 664. Now let's go over the type codes on the next slide. This table represents the type codes that we talked about on the previous slide. And that is the leading dash from the previous example. Again, the dash represents ordinary data, text, a program, a graphic, etc. A lowercase d represents a directory. L represents a symbolic link that contains the name of another file or directory. Lowercase p represents a named pipe. Capital S, a socket. Lowercase b, a block device. And lowercase c, a character device. Now let's take a look at some of the more common permission type codes. This table outlines some of the most common permission type codes along with their octal equivalents. Definitely information you should plan on committing to memory. So the first has read, write, and execute for both owner, group, and world. The octal code is 777, and again that grants all permissions, read, write, and execute for all users. The next, with octal code 755, has read, write, and execute for owner, read and execute for group, and also for world. 750 represents read, write, and execute for owner, read and execute for group, and no permissions for other. 700 represents read, write, and execute for owner, and no other permissions for other or group. 666 represents read and write for all. 664 is read and write for owner and group, and read for other. 660 is read and write for owner and group. 644 is read and write for owner, and read for group and world. 640 is read and write for owner, read for group, and no other permissions for anyone else. 600 is read and write for owner only, and 400 is read for owner only. We're not quite done with permissions yet, so let's move on and take a look at some special permission bits. SUID, or set user ID, is used with executable files. It instructs Linux to run the program with the permissions of whoever owns the file instead of the user that runs it. So if you own a file as root and set the SUID, anybody who runs that program will run it with root privileges. Now this is something you probably don't want to do very often. This permission bit is set with the lowercase s in the owner's execute bit position. So from our previous slide, we know that this is the first group in the permission string and would read RWS instead of RWX. SGID, or set group ID, sets the group of the program to the group of the file. It's represented by a lowercase s in the group's execute bit. And setting the sticky bit allows the owner, directory owner, or root to delete files in a directory. This is set with a T in the other execute bit. SUID and SGID do have their security risks, so don't set files this way unless you're absolutely sure that you have to. Now you're probably wondering how to change the permissions or mode of a file. Let's review that next. Inevitably, you'll need to change permissions for your files and directories, and for that you use the chmod command. The syntax is chmod space options space mode space file name. The options are the same as for chown and chgrp, particularly the recursive option, but you're most likely to use this command with the file's mode, either as an octal number or an octal code, like those we just covered. This table outlines some of the more common codes that you can use. Basically, you take one or more codes from the first column, add an operator from the third, along with one or more codes from the last. The first code we have is U, which means owner, G for group, O for world, and A for all. The operators are add, plus sign, remove, which is a minus sign, and equal to. The permissions are read, write, execute, and set user ID and set group ID. And these continue on the next slide. As an example, we could type in chmod space 0 plus x space myfile.txt. And that just says to give everyone execute permission to the file myfile.txt. Continuing from our previous slide, we only have a few remaining permission to modify codes. We have T for the sticky bit, U for the existing owner's permissions, G for the existing group's permissions, and O for existing world permissions. Next we'll cover how to set the default mode and group. So we know that when a user creates a file, that user becomes the default owner and the default group is the user's primary group. But default permissions can also be configured with the user mask or umask command. Umask is expressed in octal mode, and it's designed to increase system security by automatically removing certain permissions from the default settings when a file or directory is created. Those defaults are 777 for directories and 666 for files. Now you can also set umask values in etc profile, but they can be overridden. Most of the time the default is 002 or 022. And the way to set umask is to take the octal value that represents the bits you want to remove from your directory or file permissions. So if you take our default umask of 002, let's go through the example on the screen. Now remember, permissions are read, write, and execute. And because 0 is listed for the owner, no permissions are removed. And that's why you see 3 dashes in the 3-digit owner group. But since 2 is listed for both group and other, write permissions should be removed. Thus you see the W's indicated. The result is the same permissions for owner, read, write, plus read for group and others. And if we look at the directory example, the default is all permissions or read, write, execute for everyone. And if we remove write access for group and other, we end up with read, write, execute for owner, and read and execute for group and other. Now initially I thought the calculation was a simple subtraction, but it's really not. Any bit that's set in umask is removed from the final permissions for new files. But if a bit isn't set, its specification in umask doesn't change anything. Another thing to note is that if you want to see your current UMask, you can enter UMask by itself at the command line. Let's move on and take a look at some typical UMask values. This table shows some possible UMask values and their associated permissions. But again, you need to understand the process that we just reviewed for how to calculate these values for yourself. Permanent values can be set in Etsy profile, but individual user configurations can override these settings. And similarly, if a user wants to change their group, they can do so with the new-grp-l command. Now let's take a look at some UMask values. The first UMask value, 000, has a file value of 666, which represents read and write for owner, group, and world. For directories, the value is 777, which represents read, write, and execute for everyone. UMask 002 has a file value of 664, and that represents read and write for owner and group, and read for world. For directories, the value is 775, and that represents read, write, and execute for owner and group, and read and execute for world. 022 is 644 for files, and that represents read and write for owner, and then we have read for group and read for world. 755 for directories represents read, write, and execute for owner, and read and execute for group and world. 027 has a file value of 640 and represents read and write for owner, read for group. For directories, it's 750 and represents read, write, and execute for owner, and read and execute for group. 077 has a file value of 600, and that gives only read and write to the owner. For directories, it's 700, and that gives read, write, and execute to the owner. And the final value is 277, which has a file value of 400, which means read only for owner, and 500 for directories, which means read and execute for owner. Let's go back to our terminal window and take a look at our current UMask value along with the contents of Etsy profile. And now to determine our current UMask value, you simply type in UMask at the command line and hit enter. So we see that we have a value of 3 leading zeros and a 2, which can be shortened to 002. That gives us a permission of 664 for files and 775 for directories. 664 will give us read, write for owner, read, write for group, and read for world. Then for directories, I think we've got read, write, execute for owner, read, write, execute for a group, and read and execute for world. Now, if you wanted to make changes permanently to a UMask value, you would have to do so in the Etsy profile file. Let's take a quick look at the contents of that file, just to get an idea of the types of other settings that are there. So let's type in cat space Etsy profile and hit enter. And you can see that some of the other information in here that can be set for individual users. And you have some description information here in the comments to tell you exactly what type of information will go in the Etsy profile file. Now let's head back to the presentation. In addition to all of the permissions that we've covered so far, certain Linux file systems have additional attributes that you can modify, and you do so with the command chattr followed by the attribute and an operator, and then the file name. The first attribute is append only, which is abbreviated with the lowercase a, and that disables write access except to append data. Compressed is abbreviated by lowercase c, and that automatically compresses data written to the file and uncompresses it when it's read back. The immutable attribute is abbreviated with the lowercase I, and that disables write, delete, rename, or link access to a file. So for example, we could type in the command chattr plus a space myfile.txt, and that would disable write access to that file except if we wanted to append some data. Continuing with our attributes, the data journaling attribute is abbreviated with the lowercase j, and that journals data written to the file. Secure deletion is abbreviated with the lowercase s, and that zeros data blocks when the file is deleted. This is good for security. The no tail merging attribute is abbreviated with the lowercase t, and this disables merging of tail file data. No access time updates, abbreviated with the uppercase A, doesn't update the access timestamp when a file is accessed. And with that, we've concluded our lesson on managing user resources with quotas and permission. Let's review what we learned on the next slide. At the beginning, I know this looked like we were in for a relatively painless lesson. But permissions in particular are a difficult concept to grasp, but I hope you've come through with a much better understanding. I personally spent quite a bit of time trying out the different permissions and calculating UMasks. This information is essential for the certification exam. To recap, in this lesson we covered disk quotas and how they can be used to manage hard disk space usage. We moved on to learn how to set and change file ownership and permissions, including the different bits, octocodes, and commands. Thanks for watching, and I'll see you in the next lesson.